Imagine a computer that could solve the world's biggest problems. A computer that could simulate novel materials to help sequester carbon from the Earth's atmosphere, or help us develop new low-cost fertilizers that require less energy and less fossil fuels to produce. Now, there isn't a conventional supercomputer on Earth capable of solving these problems. But quantum computing is a new form of computation that harnesses the power of quantum mechanics and is expected to solve problems beyond the reach of today's classical computers.
I don't know about you, but I'm completely mind blown to hear IBM talk this way about quantum computing. And not just IBM, all the big boys of the tech world have been talking about it. Here's Sundar Pichai.
So what's exciting about quantum computing and why we are so excited about the possibilities is it'll allow us to understand the world in a deeper way. We can simulate nature better. So that means simulating molecular structures. So maybe we can discover better drugs. Understanding climate in a deeper way so that we can predict weather patterns and tackle climate change. We can design better batteries. Nitrogen fixation, which is the process by which we make the world's fertilizers, accounts for 2% of carbon emissions. And the process hasn't changed in a long time because it's very complicated. Quantum computers one day allows us the hope that we can make that process more efficient.
And Satya Nadella.
So I do think it's still a ways away. It's not here today, but I think the interesting thing is the software stack that needs to be built for quantum is getting built actively. In fact, if anything, the fact that you can simulate quantum algorithms on classical is one place where we can, in fact, already start benefiting.
But what really is quantum computing? How is it any different from the computers we already have in use? Why are companies and countries pumping in so much money into this technology? Is it really the future of computing? Are the claims of being able to solve the most complex problems overstated? Which are the countries that are in the lead of the quantum computing race? How does India fare? What is being done now that a national quantum mission is in place? Let's find out these answers from a global expert and one of the people steering India's quantum ambitions. It's Tuesday, July 23rd. I'm your host, Diya Rekhi, and you are listening to Quantum Computing, Understanding Qubits and the Future, only on the Morning Brief from the Economic Times. For a primer on the subject, I spoke to Dr. Robert Souter, or Bob, who is the Vice President and Practice Lead for Emerging Technologies at the Futurum Group. He also spent more than 2 decades at IBM Research in New York, where he worked on and led efforts in AI, quantum computing, optimization, mathematical software, and blockchain. Here he is breaking down the fascinating and complex world of quantum computing, one qubit at a time. I just wanted to start off with asking you what the difference is between quantum computing and classical computing.
It's a wonderful question because quantum computing has attracted so much attention over the last nearly decade, right? And in fact, quantum everything. There used to be a television show called The Quantum Leap. There are movies about quantum mania. And it's one of these topics that people are just attracted to. So the primary difference is what we call classical computers. And these are the computers, the processors that are in your phones and your laptops, desktops, servers and data centers, essentially pretty much all the computers we use today. At the lowest level, we deal with zeros and ones, and these are called bits. But nevertheless, even though computers have gotten extremely impressive over the last few years, there are some things that are just still beyond our reach. We need a different model for computation. And quantum computing is one of those. It's based on quantum mechanics. And quantum mechanics is the part of physics that controls the very, very small. So, for example, what happens with electrons inside atoms or photons of light, they have these quantum properties. And it turns out that if we can control those, just like from the little zeros and ones, we can build great big computers. If we can control those, we can build up a quantum computing model. Now, the difference is that these single units of information, instead of being zeros and ones, instead of being bits, we call them quantum bits or qubits. Each qubit has two pieces of information. Every time we add a qubit, we double the amount of information. So we go from 2 to 4 to 8 to 16 to 32, and by the time we have 10, 1024. So these quantum computers grow literally exponentially in power and in the amount of information we have to represent. Now, the programming model is completely different. You can't just take a classical program and run it effectively on a quantum computer. But there's hope that for some of these very hard problems that are just intractable for classical, we hope to be able to do them using this other style, this quantum style of computing.
I was reading up a little bit about what people feel about quantum computing, and I came across someone who basically said that properties and the promise are enormous, but we are yet to see real sort of tangible results. Would you agree?
I would agree in the sense of what I would call practical, tangible results. And the problem is that the quantum computers we have today are simply too small. So I mentioned qubits before. Most of the vendors that provide quantum computers have, let's say, 20 to 50 qubits. IBM has been out ahead last year. They produced a chip with 1,100 qubits, but really they're focusing on a little bit more than 100 qubits. Well, okay, that's interesting, but we need about 100,000 qubits. Maybe we need millions of qubits to solve these hard problems.
Can you tell me very simply about the complexity of setting up something like this?
When we make quantum computers, there are many different considerations. So I know I keep bringing up this qubit, these quantum bits, but everything is focused on these qubits. They have to perform extremely well. That is, when you're using them, you have to minimize the number of errors that start coming into them. Quantum computing, as I said, is based on quantum mechanics, which is how nature controls very small things. So if you try to do a quantum computation in many of the ways people are designing them, and you shine a flashlight at them, the flashlight will destroy the computation, right? If you, in some of these types, if there's too much heat, it will destroy the computation. So they're very sensitive in many different ways. And again, it depends on how you do this. So you have to control the quality of the qubits, that is, reduce the number of errors, but you also have to produce a lot of them. So there are many dimensions, of which these are 2 dimensions, quality and scale, that we have to try to improve.
Right. From your vantage point, I also wanted to understand about which are the companies that you feel are truly ahead or have a real head start in the quantum computing race. I mean, IBM is a clear leader in that sense, but apart from IBM.
The quantum industry is quite unusual compared to many other industries. We have the giants like IBM and Google and Microsoft and Amazon who have done very good work in this quantum area. And then there are a lot of very small companies, most of which are startups. We have IonQ and Quantinuum that are well-known companies that are doing something called trapped ion companies. We have Inflection, a company I worked for 2 years after IBM, Qera, Pascal in France that do so-called neutral atom quantum computers. Like IBM and Google, you have smaller companies taking a superconducting approach to this. To name one in Canada, Nord Quantique is doing this. Alice and Bob, interesting name for a company, in France. and so forth.
Right.
And so we can march down and name several of these, but it's a very rich selection of what I think are very good technologists working on this.
We've spoken about the companies, but we're also seeing a lot of countries sort of really waking up to the potential that quantum computing really holds and the future of quantum computing in a sense. So,
Mhm.
from your perspective, which are the countries that are clearly in the lead and have quite a head start on the others? And which are the countries that are catching up?
So among the leaders, the United States is quite advanced. The UK is quite advanced. France is quite advanced in what they're doing. Germany, Australia. India is very advanced, just to jump to that, in terms of users of quantum computers. Finland is doing extremely well. Denmark is doing very well. But really,
Sure.
I would say the top three are the US, UK, France, and I'd include Japan in there too. Make
I'm
it four.
surprised you didn't include China. Is there a reason why you've left China out? Because I mean, by a lot of metrics, China is also pumping in a lot of investment into quantum computing.
I omitted it because we just don't know for sure, right?
Right.
It's not as open a media approach. All the best you can really say is that, well, they state that they do this, they do that, and whatever. That's why I tend to, not include it in the list simply because I can't prove it.
You're not sure. Yeah,
I'm
yeah.
not sure and I can't
You
prove it.
can't be sure. Yeah. According to industry stats, worldwide investments in quantum technologies from the top 12 countries was estimated to be about $38.6 billion. In 2023, China invested about $15 billion. In contrast, India invested only about $0.74 billion. But now, India really wants to take that quantum leap. Last year, India launched the National Quantum Mission with a budget of about 6,003 crore rupees for 2023 to 2031 to bolster India's capabilities in this cutting-edge field. Just FYI, the largest quantum computer is being built in India by the Tata Institute of Fundamental Research or TIFR in collaboration with the DRDO and TCS, and it will have about 6 to 7 superconducting qubits. But the National Quantum Mission has some ambitious targets. It aims to deliver intermediate scale quantum computers with 50 to 1,000 physical qubits by 2031. Is this a realistic target though? Can India catch up to the US and China? Who better to ask than the chair of the mission governing board of the National Quantum Mission, Ajay Chaudhary, who many of you might know as the co-founder of HCL and the EPIC Foundation. Listen in as he takes us through all that's happening in the field in India. I just wanted to start off with asking you about something you had said, which I thought was interesting, which was about how India is about a decade behind in quantum computing. I wanted to ask you a little bit more about why you feel that way.
Well, basically, if you look at what the mission has set out to do, there are four pieces of the mission. Number one is quantum computers and the layers on top of that, then quantum communication, and then sensors, etc., and then materials. So if I look at all the four areas, in some areas we are about 8 to 10 years probably behind. But in some areas, we are really at a very good stage already, like in the quantum communications area. And the rest of the areas, we are maybe 2 to 4 years, 2 to 5 years behind. So average, I would say it's the range is between 2 to 10 years.
Sure. And when it comes to the mission as such, you are the chair of the mission governing board. And I wanted to understand from you about what your vision is for the quantum computing mission.
So basically, when the government decided to set up the mission, it was set up within the Department of Science and Technology. And they had originally created the whole concept along with the principal scientific advisor and Niti Aayog. So when it finally got approved last year, they set up the national mission around January when I was asked to chair it. And very clearly, targets were defined for the achievement of the different pieces of the mission. And these targets range from each area, there are separate targets. And these are all available publicly. So the whole idea was that in an 8-year time frame, we will achieve those targets. And in addition to the 4,000 crores that has been provided as a budget for these 8 years for DST and NQM, there is another 2,000 odd crores that is being spent by Department of Space, Department of Atomic Energy, and Department of Defense.
Sure. You mentioned this whole 8-year sort of timeline that you have in mind, possibly less than 8 years. I just wanted to also understand how realistic that would be, because I know that one of the targets is to have 1,000 qubit computer in the next 8 years, right? But as far as I know, what we are working on is 7 qubit, the project that is being handled by the Tata Institute of Fundamental Research, if I'm not mistaken. So 7 to 1,000 seems like a huge jump to me as a regular person. So I want you to weigh in and tell me, how realistic is this target?
Well, as a matter of fact, we should achieve it much faster. But let me tell you, pre-NQM, there were a couple of plans that were created by DST. And under these programs, by the Nano program as well as the Quest program, that helped to create the capability for quantum computing and quantum communications. So this pre-NQM work has really helped us. We are not starting from zero. Okay.
Hmm.
Now, since we are not starting from zero, 7 is a very good number, I would say. So now, why are we still at 7? Is because the funding available was very low. And if you talk to TIFR and Indian Institute of Science, both of them have achieved around 7 qubits. The reason was that they did not have enough funding to, put resources behind making this happen. Now, with the NQM funding that will be available, they can go much faster.
But I was reading up a little bit about the kind of challenges that come with these kinds of building these kinds of computers and developing them. One of them being, extremely low temperatures, also, this whole isolation issue. So I wanted to understand a little bit more from you on the challenges that could come up while developing these computers.
You see, when the original plan was created for the NQM, the technologies that were available were different. Today, there is a greater movement towards even silicon-based quantum computing. And if you look at this is called silicon-based quantum computing, it's called spin computing. And under the spin qubit plan, you can actually create quantum computers at normal temperatures also. And even Intel has announced very big programs for creating quantum computers at room temperature.
I know that quantum communication takes advantage of the laws of quantum physics to protect data, but I wanted to ask you a little bit more about what being quantum safe or quantum secure really means.
If you look at the current technology that is used in cybersecurity, it is called RSA. This RSA technology can easily be broken by a quantum computer, for example, sitting in China. But we don't know the status of a quantum computer in China, so we can't predict when this will happen. It could happen in 2 years, 3 years, 4 years. And if that happens, then a country like China could bring down all our financial systems, all our electric grids, our telecom systems, etc. So one of the major things that the country has to do is to start making itself quantum secure. And in the United States, President Biden passed a directive 2 years ago telling all the critical organizations to start becoming quantum secure. So they have already started that work. And in India, we are at this moment at a space where various agencies in the country are seriously looking at making themselves quantum secure.
Sure. It is very crucial now for the private sector in India to step in when it comes to quantum computing. So, why is it that we're not seeing more, audacious bets from, say, the Tatas or Reliance or, these big conglomerates that we have in the country? How necessary is it for them to put their money here? Because semiconductors, them putting their money is a pretty safe bet. Whereas quantum computing is a little bit more high risk. But I wanted to get your opinion on this.
That's absolutely right. But in NQM, we are not going to let it lie there. First thing that we have done is that we reached out to all the startups who have been working in this area. And that's all private money or VC money. So
Sure.
we reached out to them, and out of them, close to about 14 startups, the key team of NQM, all of us sat together for 2 days talking to these startups and figuring out what and how we can help them to scale. Today in the country, there are close to about 50, 60 startups who are already working on quantum computing and quantum communications. And some of them have already gone commercial and are selling their product in India and abroad. The second part of the private sector involvement is something that we just started 4 weeks ago. We called about 7 large technology companies in India, like HCL, TCS, Mahindra Tech, all of them. And we were quite pleasantly surprised to find that a few of them are already working on quantum technologies. So what we want to do is to encourage them to increase their spending on creating products out of what they are doing today. And they all feel that, yes, it makes sense for them to start looking deeper into quantum. And we are going to encourage them to work deeply also with some of our thematic hubs.
Quantum computing is very much a work in progress. Globally, there's a lot of work still to be done to make quantum computing a ready-to-use, commercially viable reality. The IBMs and the Googles of the world see this as the next big thing and are doubling down on their investments in this space. For India, it's just one of the many digital empowerment ambitions, along with building semiconductor chips and just being self-reliant. There is a long way to go and a lot of catching up to do. But nevertheless, a solid start has been made, but private investment has to follow to really make up the distance. Because after all, who doesn't want answers to complex questions, right? A chance to help with climate change and even make better shampoos? Sign me up. God knows we need them both. Thank you, Bob and Ajay. It's Tuesday, July 23rd. I'm your host, Diya Rekhi, and you were listening to Quantum Computing, Understanding Qubits and the Future, only on the Morning Brief from the Economic Times. This episode was produced by Vinay Joshi and sound was designed by Amrit Redji. Executive producers for the episode, Anirban Chaudhary and Arijit Burman. Do like, share and subscribe if you enjoyed the episode. The Morning Brief drops every Tuesday to Friday on a listening platform of your choice. Keep listening and enjoy the rest of your week. All clips used in this episode belong to their respective owners. Credits are mentioned in the description.